Hi, my name is Nelly, and I'm speaking to you from Singapore. I hope that you have been enjoying Beyond IID so far, and let me first thank you for showing interest in our work and stopping by to hear about the details. This is a joint collaboration. Carlos Parazziari is a postdoc in the group of Professor Dan Brown in UCL London. Marcel Goyle graduated last year from FU Berlin as a PhD in the group of Jens Eisert. Marcel is our expert on many-body localized systems. He is currently working at Atmosphere, which is a non-profit organization that has the goal of mitigating carbon offsets. Paul Boas is finishing up his PhD at the FU as well, hopefully defending soon. Um, Paul and a student of Carlo are actually presenting lightning talks in this conference, which I hope you will tune in for. Professor Jens Eisert is based in FU Berlin, where I recently finished my postdoc, and now I have moved to NTU Singapore. So before I begin, let me make two announcements. The first is that I want to pass on this awareness about carbon cost associated with scientific research, which Marcel has educated the authors of this paper about. So for most of us theorists, I think the carbon cost of our research is minimal, except that we do travel quite a bit. So I find this a good conscious exercise to do when we were doing an accounting for the project. And of course, we are thankful that we can gain an audience in Beyond IID without further increasing carbon emissions. So if you're curious as to what this exercise is all about, check out this GitHub where Ryan and Marcel have figured out the protocol. And the second announcement is that I have currently moved from Berlin to Singapore and I'm starting to build my own group here. So I'm on the lookout for PhD students and postdocs to work on quantum information, resource theories, thermodynamics, many-body physics. If you are interested, please apply by writing to me. So coming back to the topic, when I pitch our work in the lightning talk, I mentioned that we think that using tools of finite size analysis in quantum information actually has great potential for applications in many-body physics. And this is actually already true since many techniques have already been used and are very well familiar to the community. So what we're hoping is that this talk continues to encourage quantum information theory people to think more about how other tools in quantum communication and in information are well suited for the upcoming challenges in many-body physics. So in this extended talk, I will tell you about our first particular attempt in this direction. And we talked about the importance of studying how stable many-body phenomenon is, as well as we scale our system up in size, and in particular, thermalization mechanisms. So here, let me back up a little bit by first giving some history of the context of this problem of thermalization. So what we now understand in thermodynamics is that even when you have a global pure state which evolves unitarily, one can still have a notion of ergodicity when you look at a limited amount of observables on the time infinite average state, especially if your observables are local. As so, many results on thermalization have been identifying conditions on many-body Hamiltonians to say when ergodicity holds. For example, the eigenstate thermalization hypothesis, if anyone is familiar with that. And the nice thing is that these conditions are quite generic, so they hold for a large class of Hamiltonians. But on the other hand, many-body localization is a particular class which has attracted some interest because what happens there is that we don't actually meet these conditions anymore, and therefore even the simplest local observables, they equilibrate, but they do not thermalize according to the Gibbs ensemble. So we mentioned that there is a general recipe to construct these Hamiltonians in general, where one starts with a Hamiltonian which is easy to analyze due to symmetry, for example, being translation invariant, and that allows you to simplify the analysis a lot so that you can study it analytically. And there's a second part, which is usually a contribution that comes from impurities that break translation invariants. And that is done by introducing on-site potentials which are randomized across the lattice sites. Then it's extremely hard to make statements about the dynamics of the system according to these randomized lattice structures. So a very nice example is taking the Heisenberg chain, which has nearest neighbors interactions between the X, Y, Z Pauli operators, and then adding a local disorder term here, which is then governed by the Pauli Z. H is a real number, which is drawn randomly between plus minus 1. And delta then governs the strength of the overall interaction. So such Hamiltonians are easily generated in optical lattices, and then you can tune the strength of the disorder. So picking an initial random state, pure state, we can look at the time infinite average of the state. So most of this time, the initial state doesn't really affect the final result. And for Hamiltonians where the second term here is negligible or is smaller than a threshold, then we see behavior of thermalization, where the reduced state of a local region looks as if it was very close to the reduced state of the global Gibbs state. As the disorder strength becomes large, then the system undergoes kind of a phase transition, where the reduced system looks very far from Gibbsian. And this is already true on the level of local observables, for example, expectation values of the Pauli Z on a single site. What's more, if we look at the statistical distribution of the global energy levels, then we observe that they correspond to two different types of probability distributions. In the ergodic region, we have the Wigner-Dyson distribution, and in the MBL region, we have Poissonian statistics. And the entanglement between a reduced region R and the rest of the chain is also qualitatively different across these phases. But the mechanism of this transition is not really well understood in this field. So we use resource theories to study a particular problem of interest in this field, which is how robust MBL systems are when they interact with external small bars. And this question is important because it tells us how stable the MBL phenomenon in the context of two aspects. So first of all, naturally no system is fully isolated in practice. So the question is how extensively can this phenomenon survive in the lab? But also even on a theoretical level, for isolated systems, as your chain grows large, then it's quite probable that you have small regions in your chain which can consecutively have small disorder. And it might be possible that these small pockets are already enough to thermalize the rest of the chain. So some people would express the doubt that perhaps maybe MBL is just a finite size effect that you find in small systems, but it will never be seen on a large scale in bulk materials. And indeed, this is a heated discussion in the MBL community. So people on one have written papers about MBL being really robust under heat exchange with bars, but also some people argue that MBL phenomenon can only be really observed in finite time. So perhaps part of the problem is that most of these works have also been very limited to numerical studies or very specific modelings, and that helps very little in elucidating qualitatively what is going on. So we decide to use a more unorthodox approach to this problem. And the first thing that we have to do is to set up a generic thermalization framework that models the system undergoing a series of stochastic collision processes with an explicit bus which is finite in size. And this framework would give us the advantage because most works on MBL thermalization are then modeled via a master equation with modeling dissipative dynamics, and hence that automatically assumes an infinite path. So again, to recall, given a lattice with its Hamiltonian, we look at thermalizing a small reduced region R where the infinite time infinite average state is non-thermal and it's given by omega r. So note that when we are in the low disorder phase, this is already close to thermal. We don't need to do anything. But for the NBL phase, this is athermal. And we want to specify what bath is allowed. So here we pick a bath which has n copies of the Hamiltonian, identical with the respect to the region R. Now, of course, the question of more general baths is very interesting, but it also makes the problem non-tractable. And for a first step of the analysis, we have made this simplification. Moreover, this is actually a relevant bath, Hamiltonian, for experiments. And of course, given system and bath, we want to be able to model stochastic collisions between them, especially in a way which is energy preserving. So this can be written as a master equation, but explicitly including the bath as well. And the nice thing about this is that it of course includes random unitary channels where each unitary is energy preserving. So lastly, we need to settle on how to define thermalization. And the first thing to note here is that we are using the strongest measure, namely trace distance, instead of just looking at the local observables. And moreover, we require the entire bath end system itself to be epsilon close to thermal. And of course, you can otherwise use a single copy of the bath while forgetting about the bath and always performing the thermalization exactly with just one copy of the bath system. So given this definition of thermalization, then we are interested in the minimum required amount of bath copies that allows us to thermalize the region up to some error epsilon. And this quantity we call n epsilon. So in this paper, we present two results. And the first result is a sufficiency condition. Namely, we identify a map that allows us to thermalize with a particular number of bath copies, and then we lower bound the error, which in turn gives us also an upper bound on n epsilon. So let me quickly also mention some properties of the map. It produces the steady state or the output state where omega r is kind of uniformly hidden between the system and the bath copies. And the map can be seen as a random unitary channel where the stochastic collisions causes swap between region and bath states, and that occurs with via a Poissonian type of probability distribution. And of course, swaps in this case would preserve energy exactly because the bath and region Hamiltonians are identical. And another point that we see is that the steady state that we are aiming for can actually be reached exponentially quickly in terms of the collision rates. Now we need to bound the distance of the steady state from the fully thermal state. And this is where the technical convex split lemma comes in, and it translates into our upper bound on n epsilon. And I think it's really interesting that such a result, which was developed originally for limits to quantum communication protocols, can here be used as a tool towards studying thermalization. So this upper bound is a function that grows exponentially with one of the generalized free energies in resource theoretic thermodynamics, or as most of you know it better, the max relative entropy. And when we study the numerics of this quantity for the disordered Heisenberg chain, we show that as the subsystem size grows larger, the max relative entropy also increases linearly. So you have an exponential function where the input of the exponential would also increase linearly with subsystem size. Now, if this were a lower bound, then we would have a statement about NBL robustness, namely that we actually need many copies of the bath in order to perform this thermalization. And in fact, we show that a lower bound is actually also provable, which is our second result. And this is derived by identifying conditions on the Hamiltonian on when the map in result 1 becomes optimal. So obviously we have the same type of behavior here where the bound will grow with system size exponentially. So this is a desirable step towards proving that MBL systems will be robust under thermalization. Now, nevertheless, there are two critical differences that emerge in this bound. So first of all, there's an additional error here, delta, which is incurred, that will lower the bound. And this is to account for the coherence of omega r due to coherence in terms of the energy eigenbasis. And that arises because you have correlations that exist across the boundary of the region and of the chain. So fortunately, because interactions short range, for example, in the Heisenberg chain, and also in the MBL phase, you have much less correlations across this cut. So in fact, the off-diagonal terms in the Hamiltonian in the state are decreasing as we go deeper and deeper into the MBL phase. And this is what we show when we do when we try to verify this in the numerics. We see that the trace distance doesn't really increase so drastically when we are deep in the MBL phase, even as you increase the subsystem size. Now, a second critical difference is that this lower bound holds only when a particular condition on the system Hamiltonian is met. And this we coin as the energy subspace condition. So let me try to explain this condition. So suppose the reduced state, R, is then governed by a d-dimensional Hamiltonian, which has eigenvalues E1 up to ED. We can define, for example, a vector n consisting of non-negative integers such that they sum up to a large n, whereas the weighted sum of the energies with respect to n would sum up to sigma. So we can define many such possible vectors. For example, we can define another vector m, and there's a typo here, this should be m. So the energy subspace condition is that when these two vectors are not the same, then the weighted sum that they produce should also be different. And that is the condition. So in particular, this means that we cannot have degenerate energy eigenvalues, but of course, the ESC is much stricter. The question then arises as to how likely it is to see this. This is definitely not true for translation invariant type of systems, but when we have randomness introduced on the onset potentials, then this condition would likely hold for these MBL systems, at least for very small values of n. And this is what we see also numerically. So when this condition is satisfied for the Hamiltonians, then we have a quasi-optimal solution to n epsilon naught, which is the required bus size. And what we see here is that according to such thermalization maps, then the MBL chain is pretty robust, and it requires a relatively large bus in order to thermalize it, even approximately. So I feel that this work is actually opening up further questions to pursue. From an intermediate perspective, we're still thinking about how to strengthen our statements. For example, understanding whether we can address internal dynamics instead of having external baths, or we should maybe use a different, generalized to different types of bath Hamiltonians, or maybe even just understanding how to fulfill the energy subspace condition in randomized Hamiltonians. So, but on a larger scale, I think the really interesting question is whether other tools such as randomness extraction or matrix product states can also be used to understand the problem of many body thermalization better. So with this, I end my talk, and thanks for listening.